Well, in the last video, we learned that metals bond with nonmetals through ionic bonding. The metal will become a cation, typically, and the nonmetal will become an anion. And then the two of them are oppositely charged so that they stick together due to their natural attraction for each other. But there's a different mechanism that takes place when a nonmetal bonds to a nonmetal, and that's the topic of today's video. Sometimes a compound forms when ionic bonding just doesn't explain it. Ionic bonding just doesn't make any sense for some situations. An example of that would be water. Water's got two hydrogen atoms and one oxygen atom. If you look at a normal unbonded hydrogen atom, it's got one dot, and to become like helium, it needs two dots. That would be stable for hydrogen. Helium is the closest noble gas for hydrogen. Oxygen has 6 dots, 6 valence electrons, and would need a full 8 to become stable. Now in this case, all the atoms need to gain electrons in order to become stable. If any atom gives up electrons in this situation, it becomes even less stable than it was before. So in these cases, a different kind of bond has to form. And that bond is called a covalent bond. In covalent bonding, no electrons are transferred like in ionic bonding. Instead, the electrons are shared by the two atoms in order to gain stability. So the result is all the atoms that are involved still become stable, just like in ionic bonding, but they do it through a different pathway. Nonmetals, as I said earlier, are the ones that are going to make covalent bonds with each other. So the things down in the right-hand side of the periodic table here, when they bond to one another, they're going to do it by sharing. And that's because everything on the right side of the periodic table, all the nonmetals, need to achieve stability by gaining electrons. And so they're not going to give up any electrons at all. They have to do it by sharing. There's a rule that covers all chemical bonding, and it's particularly important to think about when you're trying to imagine covalent bonding. It's called the Octet Rule. An octet is a group of 8, is what it is. Like in music, if you had a group of 8 musicians playing together, that would be an octet. Well, an octet here means 8 valence electrons. And the rule is that atoms will gain or lose or share electrons in such a way that they can end up getting a full octet of valence electrons. Now, gaining and losing electrons, we saw that in ionic bonding, but the rule also applies to sharing. Now, there are some exceptions to the octet rule. All of these exceptions are the things that have helium as their nearest noble gas. So that would be hydrogen, lithium, boron, and beryllium. But we really only have to worry about hydrogen. And here's how we have to think about hydrogen. Hydrogen has one dot. Its closest noble gas would be helium, which has 2 dots. So hydrogen needs to have 2 electrons. Typically, because hydrogen's a nonmetal, it's going to do that by sharing an electron to fill up that extra space there and become stable. So back to our water example. How can these atoms gain stability? Remember, the hydrogens need 2, the oxygens need 8. Well, if one of the hydrogen atoms shares its valence electron with one of the lone valence electrons on oxygen, that would satisfy its need for stability. There's another lone electron in oxygen's structure that the second hydrogen could share with. So if these things can move into proximity of each other, move close enough that they can sort of hover around that pair of electrons and both share that pair, they'll both become stable, kind of like this. In this situation, now we see, if we look at the hydrogen on the left-hand side, we see that it's sharing a pair of electrons with oxygen. Never mind that it's a shared pair. To that hydrogen, that represents stability. That's the structure that helium has, and so that would be stable. And the same thing is true for the hydrogen on the right-hand side of the oxygen. It's sharing a pair to gain stability. And if you look at the oxygen, well, it is now surrounded by 8 electrons, a full octet. So for oxygen, that's stable because that's the electron structure of neon, which is its closest noble gas. So by sharing these valence electrons, both of these elements were able to gain stability. The attraction that each nucleus has for the shared electron pair is what we call a covalent bond. Here's the difference between covalent and ionic bonding. Ionic bonding is like you hanging around with your friends. You hang around with your friends because you actually like your friends, and you have some sort of an attraction of some kind for each other. Now imagine that you have a different situation. For some of you, this might not be imaginary. Imagine that you have a twin sister and you hate your twin sister. You can't stand her. So you naturally don't want to spend very much time with her. But then imagine also that you have a wealthy relative who gives you a really nice car, but with one stipulation. The car is for you and your sister to share. You can only use the car if you're using it together. Well, now you find yourself, even though you don't really like your sister necessarily, you find yourself spending a lot of time with your sister because you're attracted to the car and she's attracted to the car. That's a mutual attraction for a third object. And that's what a covalent bond is like. In this example, the hydrogen and the oxygen aren't naturally attracted to each other necessarily, but they both are attracted to the electron pair that they share, and that's what makes the bond. That's what causes them to hang around together. When covalent bonding happens, you don't get a crystal like you did in ionic bonding where a number of individual atoms stack up into some structure that might be large or might be small depending on how many are there. Instead, you get a brand new fundamental particle, and it's called a molecule. You've probably heard that word before. A molecule is just a unit of atoms that are bonded together through a covalent bond. So this water here, this structure of water, that's a molecule of water. Let's look at some other examples to get an idea of how this can occur with lots of different nonmetals. This is an example of something called methanol or methyl alcohol. It's made of carbon, oxygens, and hydrogens. There's sharing there, and there, and there. Every place a pair of electrons is shared, a bond forms, and the bonds are represented by sticks in these diagrams. Here's ammonia. Ammonia is one nitrogen bonded to three hydrogens. You can see by looking at the nitrogen that it needs to share in three spots. The hydrogens each need to share in one spot, so the natural process is that these hydrogens are going to share their single electron with the lone electrons that were in nitrogen and make this molecule. Here's another example, chlorine gas. Each chlorine atom here in this pair needs an extra electron. If they share that lone electron, well, they can gain stability and form a bond. Hydrogen gas. Each hydrogen needs another electron. If they share their pair, then they make a stable molecule. So just to review, what's formed here in all of these cases is something called a molecule. Not a crystal like ionic compounds, but an individual molecule. If there's a crystal of something that's bonded covalently, well, it's just a cluster of molecules. It's not ions that are attracted to each other. Each molecule will be identical. The Cl2 and the H2 that we just saw are examples of what are called diatomic elements. Diatomic elements, when they're by themselves, when they're not part of a compound, they always form a diatomic molecule. So H is always H2, Cl is always Cl2. But when they're in a compound, the subscript on these elements might be something other than 2. So hydrogen is always H2 when it's by itself, but in the compound ammonia that we just saw in one of our examples, the subscript is 3. So it's possible when it's bonded with something else to have a different subscript, but alone it's always 2. There are 7 diatomic elements, and here's what they are. Nitrogen is 1, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. Those are our 7 diatomic elements. Now you're going to have to know that list. You're going to have to memorize it, but it's actually fairly easy to memorize. 7 diatomics are easy to remember because of a fluke of positioning on the periodic table. Here's what you do to gather them all together. Start at element number 7, which is nitrogen. So remember there are 7 of them. Start at element number 7 and make the shape of a 7. So start at 7, make the shape of a 7. That actually only gives you 6 of them. Then you have to add hydrogen, and you have all 7. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen are your 7 diatomic elements.